right. Hi, everybody. I'm Jason, as was advertised before. When my slides come up. Hey, there they are. OK, cool. Yeah, I'm Jason. I'm develop it on Twitter, _develop it on Twitter, develop it on GitHub. I'm a serial library author, as some of you may know. That's self-diagnosed. I like donuts and poutine and axes, which means that I am Canadian. I also like constraints. I've been developing for the mobile web since before the mobile web was something that anyone would willfully use, which is around the time of Windows Mobile 5. I've written a bunch of UI frameworks. It's actually a serious problem I've developed that I'm trying to work around. And the reason why is because I find constraints to be interesting challenges. I have something called ADHD. You're probably familiar with that. Basically, it means that in order to do something effectively, it's best if I can hyper-focus on it. And these interesting constraint challenges provide me a situation where that's true. So I wrote Preact. This presentation is called Preact into the void zero, and that's just because I thought that was clever. And that's the only semicolon I think you'll see in these slides, and I did that for Christopher. OK, so you might be wondering, what is Preact? This is Preact in its entirety. I did remove the source map comment. And today, we're going to touch on that and that, mostly the second one. But we can't even talk about them until we talk about this stuff that's up here. And then this is a Preact presentation, so naturally, we need something in purple. So whatever that is going to be the last thing we touch on. But before we can get to any of this, we need to talk about JSX. If you're not familiar with JSX, I don't know what rock you've been living under. But secondly, don't worry. It's really, really easy to understand. JSX is simple at its core. By the end of my talk, you're going to be already starting to rewrite your entire Webpack configuration in JSX, which makes it longer and more complex, and that's a good thing. So if you don't believe me, go and look at the Webpack 2 docs. That is in them, and I have some part in that. So what is JSX? JSX is an XML-like expression that is compiled to a function call. We write the thing that you see on the left. We write these HTML-looking angle bracket, syntaxes, and on the right is what we get out of the transpiler, like Babel or Buble or whoever. There's 10 transpilers now. And the whole point of JSX, or at least the whole point to me, is that I would be totally happy writing the thing on the right. And this is verified by the fact that I'm constantly tweeted at by people who much prefer the thing on the right. And I think that's telling. I like JSX because I like the parity with the DOM. But the thing on the right is something people are perfectly happy to write. So it's important that this is kind of a transparent thing sitting in front of an understandable thing. So there is one little complexity on top of this from JSX, and it's the fact that you can get back into JavaScript from these angle bracket syntaxes. So you can see in the thing on the left, 1 and the variable world are both persisted into the code generated on the right. And then the other complexity is just if you use a capital letter as the first letter of a tag name, it's a variable reference in the resulting generated code. So the essence of JSX is this factory function we saw. It's really simple. It just has a signature that accepts the things that you typed into your text editor. So you have node name. You might see this referred to as tag name. They're the same thing, which is going to be a string or a function. Really, it could be anything, but it's going to be one of these two. You have attributes, which is optional. It could be an object. And then the rest of the arguments are children, and this is how we do composition. You might be thinking to yourself, aren't you just writing hyperscript, right? Isn't that really what this is under the hood? And you wouldn't be wrong. Hyperscript is very similar. In some cases, it is the same. It is a slight superset of JSX because of this. So hyperscript supports this additional tag syntax where you can use essentially CSS selectors to predefine attributes on the element, and JSX does not have that. So what JSX does have is the ability to use these sort of extended tag names. So it's important that we have a solid understanding of JSX because the concept is simple and direct, but it's the interface through which we access all of these virtual DOM libraries. Also, please remember that JSX is not DOM. JSX is not even related to DOM. It's just a syntax It doesn't know anything about your code or how it's intended to work. You can use this to write your Webpack configuration. Please don't. You can use this to write XML. So if you want to write a SOAP client and you don't want to deal with parsing and serialization, you could use JSX for that. And I would actually recommend that as an interesting solution to a problem. So that's JSX out of the way. Next stop on our adventure is going to be Virtual DOM. Virtual DOM is just objects that represent a DOM tree structure. That's it. There's nothing else going on. I like to think of it as configuration that you are passing to a theoretical DOM builder of some kind. And we're actually going to walk through making that DOM builder not so theoretical in a second. But the first thing we need to understand is, how do we get from JSX to VDOM? And the way that we do that is by invoking that H function that we just defined the arguments for. It's fairly straightforward. We know that we wrote our JSX, we got our H function calls. What we need to do is have an H defined such that it produces these objects. This is virtual DOM. Sometimes it gets trumped up a little bit beyond this, but at its essence, this is what virtual DOM looks like. It's just nested objects. This is surprisingly easy to do. This is how you do it. It is a one-line function. You can do some more stuff here if you want. You could normalize children. You could remove empty values, coalesce adjacent string nodes, lots of stuff. But at its core, you could totally write a virtual DOM renderer using this function. So let's do that. Let's write a virtual DOM renderer. So the first thing, we're going to pass ourselves a vnode. This is that object that we saw before up on the right there with the scroll bar. So the first thing is, we need to create a DOM element that matches the type of the VDOM element we passed ourselves. So we could do that using create element, pretty straightforward. Then we're going to loop over the attributes. In this case, there's just one ID equals foo, and set them as attributes on the DOM element. And then we got to set up recursion, so we're going to loop over children, pass them back to render, and then take the resulting DOM element and append it to our current DOM element. There's one slight complexity here that you may have noticed. One of the children is a string. One of these things is not like the other. So we need to deal with that hello text. And the way that we do that is, in render, if the vnode is actually a string, we just bail out with a text node. So that's our virtual DOM renderer. There's one slight complexity here in attributes. You notice I've called them attributes, and if any of you have used React, you're probably getting a little hot under the collar about that. That's okay. They're not attributes. Don't ever let anyone tell you that except me. I don't know why I've chosen that I can get away with it, but for the duration of this talk, I can. So they're actually props, and there's a reason why we don't use the name properties for that either. They're kind of an abstraction between these two things. So most HTML elements can accept data as attributes, and they can also accept similar, often typed data as properties through something called DOM property reflection. But both of these are technically wrong, because there are things we can do with attributes that we can't do with properties, and there are things we can do with properties that we can't do with attributes. So what we need is a way to have both. And thinking about Preact sitting at 3 kilobytes, you can't use whitelists in Preact. If you've seen libraries that define, like, here are self-closing tag names or whatever, that's not a thing that Preact could ever do. There's not enough room. So what we do instead is we have a reference to a DOM node, and we actually ask the DOM node, do you have support for a property foo? And if it does, we use the property. If it doesn't, we fall back to setting the attribute. This actually works really well for things like custom elements, because custom elements tend to define getter-setter pairs for properties, so we just kind of use those and move forward. So the question that you may be asking yourself is, does it work? Sorry, I have a really bad Sean Connery impression. I promised somebody I wouldn't do that, and then I had to do it in order to break that promise. So here's the virtual DOM that we wrote. We're going to pass it through the render function that we wrote, which gives us back a DOM node, and we're just going to chuck that into document.body. On the right here, tethered through my phone, it worked, yay, is the output in JS Fiddle. So it works. Deploy it to production. Just be thankful you don't work with me. So we just built a simple virtual DOM renderer. It is a terrible virtual DOM renderer, and I'm sure you were probably all aware of that as we were writing it. It's a version 0. But it's terrible because it doesn't diff. It doesn't look at the current state of the DOM and update the DOM to reflect anything. It just blows away the whole DOM and replaces it with something. Diff algorithms in virtual DOM are kind of the subject of a little bit of debate and mystery. The debate is warranted because there are trade-offs here that you can't treat as black and white things. But the mystery is unwarranted, and I'd like to attempt to demystify that for you guys today. So diffing is basically this idea of, instead of rendering top-down and creating a new as we render top-down, we're going to pass ourselves a reference to what the DOM looks like now, and then mutate it to look like what this JSX derived DOM looks like, our virtual DOM. Just apply the differences. So on the left, you can see what virtual DOM looks like. This is this object we've been staring at for 15 minutes now. On the right, you can see what the actual DOM looks like. And you can see that the names are the same or similar. There is actually a DOM children property. It just doesn't include text nodes, so we don't use that. But you can see how you could probably run through this and perform a comparison left to right and apply the changes on the right. So it's basically a 3-step process to run through the diff. The first step is type. Before we can do anything, we need to create an element with the correct node name. So, I mean, this is pretty straightforward, but that's kind of step 1 here. The second step is we're going to loop over the children, perform a bidirectional comparison, and figure out whether we need to add, remove children, rearrange them, etc. And then the last step is just to update the attributes / props with the new values from our virtual DOM tree. So, and then we set up recursion by looping over the children. So let's start off with type. We enter into our diff. And the first thing we need to figure out is this node owned by a component? If it's not owned by a component, things are really easy. We just look at the node type, in this case node name. If it's the same, we're just going to update it in place and be done with it. Looks a lot like the virtual DOM renderer we just wrote and then scrapped. If it's different, we're going to throw out the node and create a new one and then continue diffing down the tree, setting attributes and children and so on. If the node was owned by a component, things are a little bit more complex. Basically, we just need to create a backing instance, create it if it doesn't exist, update it if it does exist, set its props. But then things get really easy. We call render on that backing instance, which returns a new virtual DOM tree, which we just pass back into the same diff function. So I don't think this is actually even that complex. There's some intricacies here with lifecycle, but as far as a chart on a slide goes, it's pretty simple. So children is even easier than that. It's basically 3 steps. The first step is we loop over all the existing children in the DOM and put them into lists. There's an unkeyed list, which is ordered, and then there's a keyed list, which is named. The second step is we loop over the new virtual children, which are just these lightweight objects and/or strings. And we find the first match in our list of unkeyed or our map of keyed. And we find that or null, so we have either an element or nothing indicating we're going to need to create a new. And then we diff that against our virtual DOM child object. At the end, we're going to have an element that matches this sort of specification object we've got for it, and we just insert that at the current index that we're at in the virtual loop. And then the last step is the easiest. If there's any kids left, we just delete them, because they're obviously not used in the updated definition of what the DOM should look like. You might be wondering about the keyed versus unkeyed lists. This is probably the worst understood part of virtual DOM, so I really wanted to touch on it today. I tried to explain this on Stack Overflow, and it's like the only thing I've ever done on Stack Overflow, and I kind of butchered it. So let's get it done within slides. So keys are they attribute meaningful order to virtual DOM elements when they have uniform type. So we can see in this example, we have 3 list items, 1, 2, and 3. In the second render here, we only have 2 list items, and it's clear to you and I as humans that we've deleted item 2, right? The text 2 is gone, so we know logically it's probably that we deleted the second item and the third one has just moved up. But a virtual DOM renderer does not know that. There's nothing saying that item 2 is item 2 in the second render. It just receives a new tree each time. There's no way for it to correlate these things. So what it's going to do is it's going to look at 1. 1 is unchanged. That's easy. Nothing happens. It's going to look at 2, and it says, oh, no, actually, they changed the text content of 2 to 3. So that's fine. So I'll just update that. And then it's going to get to 3, and it's gone in the second render. So it's just going to kill that node. And the thing to understand here is, by default, for a list of uniform elements in virtual DOM, it will always push and pop off of the end. It has no concept of removing and adding to the middle of the child list. Contrast this with a keyed approach. In a keyed approach, we give each element a unique key. They do have to be unique. So you can see in the first render we've got 1, 2, and 3. In the second render we've got 1 and 3. It's very obvious that the element with key 2 has been removed. Now we've told the virtual DOM renderer exactly what to do, so it knows when it loops over the list, when it gets to item 2, the key is wrong, it will delete it and move to item 3, which will just move up in its place. So this actually makes things really, really simple for the renderer. It is kind of cheating. You're essentially telling the diff how to do its own job. But in the case where you'd like to control the diff, it's nice to have this escape hatch. And so the last step for this diff process, now that we've got our children and our type diffed, is attributes. This is really easy. We give ourselves the old properties and the new properties. We loop over the old ones, find the ones that are not in the new property bag, and then set them to undefined in the DOM. And then we do the exact opposite. For each new attribute, we check if it differs from the old value. So this would include if the attribute is now defined and it was previously undefined, it's going from undefined to some value. And then we set its value in the DOM to the corresponding property. So we've solved all of life's problems, and now our app is as fast as it could possibly be. Except this is completely not the case. All we've done is we've moved our problems into a library. We've moved our problems into Preact or React or Inferno or ViDOM or the list goes on. So I want to tell you guys a little bit about the performance journey I've been on in writing Preact and trying to benchmark it and take it further than it currently is. This is something that you will often see people say, especially if you hang out on Twitter for various reasons. So we often hear complaints, the DOM is slow, right? The DOM is the source of slowness. And it's true that the DOM is not as fast as an immediate mode drawing API. It's not designed to be. There are different things. But the DOM has all these advantages that if we compare it with an immediate mode drawing API, we're kind of not really taking into account. The first one is the DOM offers accessibility essentially built in. You can annotate the DOM with titles and ARIA attributes, and you're going to get screen reader support for basically free. Other platforms have ways of doing this, but the DOM's way of doing this is incredibly easy. You almost don't even need to understand how it works if you're writing semantic markup. The DOM is also extensible. People like to forget this, but if I'm using Twitter on Windows and I want to add emoji support to Twitter, I install a browser extension that hooks into every text input on Twitter, and I can now type emoji into the text input without using Twitter's input field. Twitter doesn't know about this. They don't have to know about this. They don't care about this. That is one of the values of the DOM, is it's this substrate that underpins all of our applications that is extensible without our knowledge. And that's the same kind of thing with saying the DOM is framework agnostic. You can write 2 widgets in 2 different frameworks, and as long as they are rendering elements, you can append those elements to a common parent, and they don't have to know or care about each other. So Preact, at its core, is essentially a DOM renderer. It's a virtual DOM renderer, but it's just sort of a DOM library, right? This is the next step after the whole sequence of libraries carrying on from jQuery. So I'm going to share a couple lessons that I've learned while writing a DOM library. The first is use text nodes for text. This sounds stupid. I'm aware of that. But it's surprising how often you will see this either misconstrued or misinterpreted. So the DOM has an API for working with text that we often ignore. It's create text node like we saw before. You can seed an initial value. You can insert these, you can move them around like any other element. They don't inherit from element, they inherit from node. And then you can set its text. So I've got create it, insert it, flip it, and reverse it. I think that's a Missy Elliott joke, but I don't remember. I actually had to Google the lyrics for that to make sure I was on point. So this is a benchmark showing that that is the case. We've got text content and then text.node value, just for an atomic update. Node value is clearly faster here. If you were writing a library or a framework that does text updates, you would be crazy to choose the first one. I will say text content does a lot more work. It's not unjustified in its slowness. It's removing elements that don't belong there. It's collapsing strings into a single text node. It does a lot of work. But in a lot of cases, we're using text content in a situation where we don't need any of that work. So the next DOM lesson, I think that's an Aerosmith joke, I don't know. The next DOM lesson is avoid getters, just entirely. Don't use them. Don't rely on them. Or when you are using them, be incredibly cognizant of the fact that you are. And if you're confused about what this means, here is a snippet from Chrome DevTools showing if we look at the node type property of a text node, right? Text node.node type, it should be the integer 3, which is the corresponding type. it's actually undefined on the text prototype, which is a little bit counterintuitive. It's defined on the node prototype, which is what text inherits from, and it's a getter. And this is a huge red flag that I have highlighted as a red flag. The idea is everything is going to have this inheritance from nodes. They just implement it in one place. I'm sure there's some better reason for this, but this is a red flag for anybody who's writing a DOM library. So this means that when we write code that relies on node type, by default, this is not going to run as fast as it could. Instead, we can use duck typing to improve the performance of this. So text nodes happen to have this, this function called split text. Split text is much faster because it's not a getter. All we're doing is checking if a property exists. And I know Benedict would tell you this if I didn't. You can also check to see explicitly that the property exists. The problem with the second check is actually that it's going to check if it both is existing and truthy, which is two operations where the second one we don't care about. So here's a performance test showing that that's true. You can see here we've got instance of and a couple of different variants there. Instance of is not great because if you have a text node from a different document, it's a different parent class, so it's kind of useless. The getters are all relatively slow, but those property accesses are surprisingly fast. So this is how Preact detects text nodes. The last one is live node lists. Please try not to use these. They were a good intentioned thing, but they end up hurting performance. So here's an example of trying to clear children out of a parent element. First one, you've probably seen this before. You just do a backwards loop over what appears to be an array. You do a backwards loop because the indexes are going to be all screwy if you loop forwards because it is a live node list. They change as you mutate. But we're removing the children as we go through the list. Eventually, we're going to get back to none, and then we're good. Second one is much faster, though, because we're just accessing one property at each point in the loop. We never have to go back and ask for child nodes again and recompute child nodes. We never have to access an offset in essentially an array. We're just using references. So here's a performance benchmark. One thing to remember with this benchmark is a lot of this is actually setup overhead. I have to actually create the elements before I can delete them and benchmark that delete. But in either case, last child is always faster. So talking a little bit about measurement, I've been doing performance optimization for quite a while. And back in the day, benchmarks were like, run a loop 5 million times, check the date before and after, and cross your fingers. And this is still surprisingly often the way that stuff works. But Chrome DevTools has kind of advanced this, and it's made things really visual. So DevTools is like having a little tiny copy of Sam Saccone in your browser, and you can ask him on demand to run performance tests. It's also far and away the best tab in Chrome DevTools to use in a slide. So one metric I rely on a lot is what you can see here. It's the total time taken to render a tree of components. And the value here is you can see it visually. I can see that it is 3.81 milliseconds to re-render this dbmon, I think it is, benchmark. But I can also see that it's consistently around that same value. And there's value in just being able to visualize that and track it over time. The next tool is IR Hydra by Mr. Aleph. I believe he is a V8 engineer. And this actually touches on what Lynn was talking about in her talk with deops and optimizing compilers. So I get to thankfully skip over this slide and not go over time, which is great. But really, this is just going to show you visually when your code is going to deopt. And it does this using the type feedback from your code having run. You run this with flags. And if you want to know the flags and figure out how to run Chrome with these flags to get the tracing output, go to that git.io URL. That only works on Mac OS for now. I don't know how it works on Windows yet. And then the last tool is one I wrote. This is, unsurprisingly, the first app that was built with Preact in like September of 2015, and hasn't been updated since then. So I'm sorry, there's like a whole bunch of UX flaws. But the goal with ESBench is essentially to give you a very simple user interface on top of Babel and benchmark.js. So it runs your code through Babel, and then it passes it over to benchmark.js, and you can do comparisons of various different implementations of a given function, and literally just figure out which of these runs fastest. And then you could do it in a bunch of different browsers, or you could check it as new Chrome releases come out, and you can see that, oh, Turbofan started inlining push, so now all of a sudden the benchmarks have inverted. Which is useful. It's useful to know. That way we're not doing performance optimizations and then a year down the line accidentally suffering because of them. So a couple lessons from these things. The first is be explicit. So I covered this a little bit earlier. Don't accidentally cast something to a Boolean if you have no reason to do that. So in this case, we're checking what looks like the existence of props on an object. But really what we're doing is we're checking that it exists and that it isn't 0, an empty string, null, false, etc. The second one is much more explicit. We are literally checking to see if props is defined. Reading this as a programmer, it makes a lot more sense, and it also is a lot faster for V8 to be able to run. The next lesson is inline helpers. So functions can be way too generic, and as JavaScript developers, because this is kind of a language that will let you do anything you want, this is really, really common. So this is a hook function that was in Preact. It does way too much stuff. It gets de-opted immediately, and the solution here is to rewrite it to just be an inline function call. And the last one is just short-circuiting. Here's a quote by me. It's a quote by me. But basically, the idea is if you can avoid making a function call, avoid it. Sometimes there's just no reason to do certain things. In the case of Preact, this would be like if you're diffing a virtual DOM tree and a parent element has one textual child and the DOM also has one textual child, it's actually going to entirely skip the rest of the diff, update that text child in place, and then bail. And there's a huge performance improvement. It's probably the most significant performance improvement that has ever gone into Preact is that particular early return. So the point of all this is to say, please make decisions based on actual data. Find a way to get data, whether it's a benchmarking tool or dev tools or any of these solutions. Collect better data through benchmarks and performance tests, and then act on that by setting better goals. And if I can leave you with a message, it's remember that we all have a shared goal of making the web faster and more accessible. That's how we provide better experiences to frustrated users of the mobile web. It's how we're going to make the mobile web the platform of choice, in the next 3.5 years. I just picked that number, but and then finally, it's how we get the next billion people online so they can benefit from the access to the same resources that we've had opportunities from. So that's my talk.